right, so chi-square test for goodness of fit. By the way, there are 3 different chi-square tests that you're going to learn in this chapter. So this is the first one, is the test for goodness of fit. And this is when you're comparing it to like a claim, right? So there's like a supposedly known distribution, like with the M&Ms, where the company claims a certain percent are orange or red, and we're comparing to see how good of a fit that really is to what the company claims, okay? So random sample or randomized experiment, 10% rule, you still need to check unless what? Right, if it's an experiment, you don't have to do the 10%, okay? Or if it's infinite, right, then you don't have to do 10%. And then large counts, this is different. Large counts has to be at least 5, and where a lot of people mess up on the AP test is they use observed counts instead of expected counts. You have to use expected counts. So for example, if you were doing the rolling the dice problem, and I was rolling it 60 times, and all the expected counts were 10, right, for every single one of those numbers. There are 6 numbers, so every single one is 10, which is greater than or equal to 5, so you'd be good to go. So don't forget, use expected counts when you do large counts. And you have to show your work. The other place that they set our common errors is a lot of students just say all are at least 5, and they don't actually show the numbers. So you do need to show what those lovely numbers are. So cautions, the chi-square test statistic compares observed and expected counts. Do not use proportions, use counts. All right, so like 10 of them out of the dice. When checking large counts, we just talked about that. Use expected and not observed. All right. Okay, birthdays in hockey. Did anybody read the book Outliers by Malcolm Gladwell? I did. Too bad for you guys. It's good. It's actually really good. So here we go. In his book Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it to the highest levels of the game. Specifically, because January 1st is the cutoff date for youth leagues in Canada, where many National Hockey League players come from. So players born in January will be competing against players up to 12 months younger. So who has the advantage? The older kids have the advantage, right? Because they're probably bigger. So the older players tend to be bigger, stronger, and more coordinated, and hence get more playing time, more coaching, and have a better chance of being successful. To see if the birth date is related to success, judged by whether a player makes it into the NHL, a random sample of 80 NHL players from a recent season was selected, and their birthdays were recorded. The one-way table below summarizes the data on birthdays for these 80 players. So January to March, we've got 32 of the 80. April through June, we've got 20 of the 80. July through September, 16 of the 80. And October to December, 12 of the 80. What are the expected counts, you guys? We're going to have to find those, so we might as well find them first. Yeah, it'd be equal. Expected counts is that they're all equal. And since there's 4 categories and 80 players, do 80 times a fourth. So every one of these would be 20. So we would expect an even distribution among the birthdays. So we're going to see, is that a significant difference then, right? So if everybody should be 20, 20, 20 equal, but yet we've definitely got more January through May and less October through December, we'll see if it makes a difference when you were born as to whether you make it to the NHL. So do these data provide convincing evidence that the birthdays of NHL players are not uniformly distributed throughout the year? So providing convincing evidence means we're doing a significance test. And so we need a null hypothesis and an alternate hypothesis. Who has a guess as to what the null hypothesis would be? Without looking at the book. Anyone have a guess of what the null hypothesis would be? Just a guess. Jake, what do you think? That it is true. What do we mean by true, though? Yes, we're looking for all equal, that the distribution is equal, all right? So the null hypothesis would be the birthdays of all NHL players are evenly distributed across the 4 quarters of the year, all right? And so the alternate hypothesis, just a guess, Donovan, what do you think the alternate is? Yeah, they're not evenly distributed, right? The birthday of all NHL players are not evenly distributed across 4 quarters of the year. Exact same thing, but not evenly distributed, okay? And, of course, the name of the test comes next. Owen, what's the name of the test? Chi-square test, for goodness of fit. Chi-T, test, all right? If conditions are met, we'll perform a chi-square test, and you have to say, for goodness of fit, because there are 3 different tests, all right? So for goodness of fit. Random samples, yep, we have random samples of NHL players. For the 10% rule, David S., how many do we have in our sample? 80. That means we need at least how many NHL players that year? 800. Good. So for this one, we are sampling without replacement, so there has to be at least 800 NHL players. And in this season, they didn't tell us this in the problem, so that was nice of them later to tell us in the answer. There were 879 players, so I guess we're good to go with the NHL League. All right? And the last one is large counts. Now, this one sometimes takes some time when you're doing these tests. This one wasn't very hard. It was evenly distributed, so a fourth of the 80 should be in each quarter. So you would want to say, using the expected counts, all of them are 20. Every category should be 20 if it was even, so all are at least 5. So use expected counts, all right? And now we got to do our lovely test statistic, which you guys learned the formula for. And so it's observed minus expected squared divided by expected. So this guy minus this guy squared divided by 20. That guy minus that guy squared divided by 20. If you want to write them all out, you can. You at least need to set it up like that for me, where you do the dot, dot, dot. It's fine, okay? And then you can, of course, use your calculator to find all of it. And let's go through how to actually do that today. So grab your calculator.
Can we do that?
What'd you say?
Didn't we do that?
I sort of talked about it. We didn't really do it though. I just said here's how you kind of do it. So we want to do observed and expected. So you want to label one of them observed, whoops, and the other list expected. And our expected is easy. It's 20, 20, 20, 20. And then our observed, we have to enter in the data, which is 32, 20, 16, and 12. All right, we can actually do all of the tests from the lists. So let's actually do the test in this lovely spreadsheet. If you don't have the other one, though, I think you have to go back to the main screen. Home screen, did you get yours in? Okay, and you probably got it already. Good job. All right, so on this one, you guys, if you want to do it on this screen, and I'm going to, you go to Menu. And you go to Statistics. And you go to Stat Tests. Do you guys remember which one it is? Number 7, chi-squared GOF. Okay, we will use this one as well, but for now we're doing goodness of fit. Okay, GOF. That's what it stands for, goodness of fit. All right, so observed list. I just figured that out. So you want to do observed and then expected. Degrees of freedom. How do we figure out degrees of freedom? Number of categories minus 1. So there were 4 categories for the 4 quarters of the year, and so 3 goes in for degrees of freedom. If you do click the shade p-value, it'll give you a really pretty graph. I'm not going to because it takes up some space, but it will give you a graph of that. This does not want to click. I'll just come over here and do it. Oh, maybe not. All right, you guys, so it gives us the chi-squared, which that's what we would get if we plugged it all into the formula, right, the 11.2. And then it gives us the p-value, which we could also find by doing the lower, upper, and degrees of freedom. Remember chi-squared CDF. You can also find it that way. And then degrees of freedom. You have to list all 3 of those things on your test, okay? So, again, you could do the p-value like this, chi-squared CDF. which gives us 11%, or you can use the test on your calculator. And don't forget, you must always state your degrees of freedom on the test, all right? So you guys, are we going to reject the null or fail to reject the null? It's less than 5%. It didn't give us a significance level, but we use 5% when it doesn't, okay? So because the p-value is less than 5%, we reject the null. We actually do have convincing evidence that the birthdays of NHL players are not exactly distributed across the 4 quarters of the year. Those lucky January people. Snap. All right? All right, so there you go. Follow-up analysis. So this is new. And we're going to do a follow-up analysis anytime we have significant results. Did we just have significant results? Yes. All a follow-up analysis is, you guys, is which ones made the biggest difference? Which categories screwed it up the most, right, from the normal? And so start by examining which categories of the variables show large deviations between the observed and expected counts. And then look at the individual terms that are added together to produce the test statistic. These are called components, all right? And those components, we're going to look at which ones contribute most to the chi-square test statistic. So if you look at observed and expected and you just subtract the difference, we had 12. And then if you do the part of the test where you do observed minus expected squared divided by expected, you get 7.2. All right, and you can just tell really by the differences which ones are the biggest factors. So it makes sense kind of that January through March is probably going to have the most. So we had 12 more than expected, and then the October through December had the least, so we actually had 8 less than expected at the end of the year. So the component for January to March birthdays made the largest contribution to the chi-square statistic. That's your follow-up analysis. It's like one sentence, and it's just which component made the biggest difference. You can say one or two of them, all right? You can say that January through March made the biggest difference, and then the end of the year, October through December. Make sense? That's it. Okay.